Okay, welcome to this week's colloquium. It is my pleasure to introduce Professor Lina Necib from MIT. She's an expert on galactic dynamics as a measure to understand dark matter, but she has also done some work on collider physics and model building as well. Let's see. So Lina got her bachelor's at BU and then her PhD from MIT, working with one of our graduates, Jesse Thaler, for those of you who have been around for some time. From then on, she was a Sherman Fairchild Fellow at Caltech, a Presidential Fellow at UC Irvine, briefly, and a Fellow at Carnegie Observatories until July of 2021, where she just started at MIT. Thank you, Lina.
All right. I hope this is working. Okay. So thank you so much for having me. It's very exciting to be here. So I'm excited to tell you today about how we can use stars to trace dark matter. Let's start with the overarching goal of this entire research program. And it is actually to build the local map of dark matter. And by local map, I mean local phase-space distribution of dark matter. So the reason that we can actually do this now is because of two major developments in very major areas in simulations and observations. So for a while now, we can actually simulate the universe in a box. So we start at very early redshift. We have some kind of density perturbation. We have some particles, dark matter. We teach them about gravity, and we let them evolve. And then they form into these overdensities here, where our galaxies are actually eventually going to live. But for the past few years, we've been able to actually go beyond just the dark matter simulations to include the baryons, which are quite difficult. And in particular, now we can actually have, for example, a gas map or a gas temperature here, which is important in the evolution of stars and how we can actually produce stars. Not only that, but we can also track properties of the gas, for example, the gas metallicity, which again will be imprinted on the stars. And finally, we're able to actually have very high resolution zoom-in simulations of galaxies that look very much like the Milky Way, so with the disk and spirals and everything, which is quite amazing. On the other side of all of this, we have Gaia. Gaia is a space telescope that gave us the largest stellar kinematic catalog to date. It gives us actually the kinematic measurements of 1.8 billion stars. That is over 1%, close to 2% of the Milky Way, of the stars in the Milky Way, which is quite incredible. And now I'm just zooming in and showing you a very small subset of 96 million stars and how they would evolve over the next 800,000 years. So these evolution actually that happened only over the past few years enable us to map out the dark matter. So we're going to use high resolution simulations to build correlations between the dark matter and the stars, and then go into the Gaia data and study the properties of these stars to build what we can understand about dark matter. So today's talk is how to map out the dark matter phase-space distribution at galactic scales in 4 different key locations. So let me actually first discuss why we want galactic scales. The reason for this is because, first of all, our experiments are here on Earth, which means that whatever dark matter is doing very locally is going to affect our prospects of detection. And second, it's because all the deviations from the standard paradigm of dark matter, so lambda CDM, actually do happen at galactic scales. At very large scales, dark matter behaves exactly as we think it does, but all the other issues that we end up with are closer to home, so very close to the Milky Way. Which is why it's very important for us to understand the map or the phase-space distribution of dark matter. Today, I'm going to be discussing the dark matter properties in 4 different locations, so basically a tour of the Milky Way. We're going to start in the solar neighborhood, talk about the galactic center, dwarf galaxies, and streams. However, to motivate why it is interesting that we understand the dark matter distribution in these 4 locations, I will be using one example for detection from particle physics for each one, just to make the connection between the 2 fields, for astrophysics and particle physics. But this doesn't mean that it doesn't generalize. So the map of dark matter, for example, in the solar neighborhood, it will affect direct detection of weakly interacting massive particles, or WIMPs. But what I will be saying also applies for detection of axions, for example, and low mass dark matter, etc. Then we'll talk about the galactic center and indirect detection of the galactic center. So it's important to understand the density of dark matter at the center of the galaxy, because for indirect detection, dark matter would annihilate or decay into standard model particles that we later detect. And we need to understand how much dark matter there is so we are able to actually interpret these results. After that, we can go on and talk about dwarf galaxies, where we can also discuss indirect detection in dwarf galaxies, but also how we can solve the core versus cusp problem and investigate different types of dark matter models. And finally, I will go very briefly into streams and how now that we can actually build catalogs of streams, we can look for gaps in these streams, and they can tell us about the dark matter subhalos. So let's start with the solar neighborhood first, and in general, direct detection. So direct detection, this is a xenon atom. It comes in, collides with a dark matter particle, properly colored, and this interaction produces some scintillation light that is later detected by our experiments, and this is how we know dark matter was there. However, the amount of scintillation light does depend on the incoming dark matter energy, and in particular dark matter velocity. So more formally, the rate for direct detection is proportional to the local dark matter density, rho, as well as the integral of the velocity of dark matter, which means we really need to understand the flux of dark matter, density and velocity. Unlike the local dark matter density, which has been really a focus of study for the past almost 100 years, which was quite incredible, the velocity distribution did not really have that same treatment. And in particular, it has long been assumed that the dark matter velocity distribution is just a Maxwell-Boltzmann distribution that peaks at about 220 kilometers a second. This distribution really comes from the fact that it is the simplest solution to the flat rotation curves. So you would assume that your potential is an isothermal sphere and apply Poisson's equation, and you will get the Maxwell-Boltzmann. So in that process, you had to make 2 assumptions. You had to assume that the system is isotropic and in equilibrium. And as I will show you, this is not the case, which means that what we want is really how to build an empirical velocity distribution of dark matter. And by empirical, I mean really what is the phase space distribution of dark matter very close to the sun, not on the other side of the galaxy, just because this is how it's going to play directly into my direct detection rates. So the way to do that is from simulations, correlate the dark matter velocities to that of the stars. And it's going to be some dark matter and some of the stars. Then from Gaia, we go and measure the phase space map of these stars and put 1 and 2 together, which is a lot harder than it looks, to build the new velocity distribution of dark matter. So first of all, if I were to look at one of our simulations and look at the density map of dark matter, there is a lot of structure here. And in particular, what I'm going to show you here is how to kind of go from the dark matter to the stars. But really, what I would like to emphasize is that this correlation that we will be talking about today is really it affects the velocities, not the position space. This is just kind of visually aiding what's going on. So, for example, we can take a look at one of these subhalos and then move over from the dark matter map to the stellar map. And we find out that there are some parts, for example, that one subhalo, that will be matched between the stars and the dark matter. That's not always the case, and you can see that this map here is quite different from that of the dark matter. But there will be some correlation where we can use the stars as tracers. So in order to actually show you where this correlation holds, we will be using FIRE simulations, which stands for feedback in realistic environments. And what you're going to see here is how we were going to build one of our galaxies. And the most important point that I would like you to take from here is that to form a galaxy, we have to get a lot of collisions and a lot of mergers. This is in general how galaxies form. And this one is actually one of our quieter galaxies, where at the end, at redshift 0, it looks like a spiral disk galaxy just like ours. So the Milky Way itself actually has had sustained quite a few of these mergers. And in particular, somebody can actually build a merger tree for the Milky Way. So actually from this paper, it's quite cool that they use globular clusters to figure out when each merger happened. And basically you can see that this is the Milky Way, and it's the product of a lot of different streams, like Sagittarius, Dwarf Galaxy, which is now a stream, the Helmi streams here, but also larger mergers like Sequoia, the Kraken, and Gaia and Enceladus. So there are a lot, and you can get very creative in naming things. The ones that I would like to focus on today are the Milky Way, so the older component of the Milky that has merged very, very early on with the Milky Way, and this Gaia Enceladus merger. So what is the strategy here? So this is the velocity distribution, and we're going to build it like we're going to stack things one by one. We take the velocity distribution of the stars, show you that indeed they map out between the stars and the dark matter, and then start building things on top of each other. So I'll be discussing 3 different components here. And let's start with the old halo. What I call old halo are the dark matter and the stars that have merged in prior to redshift 3. So in my simulation, I look at the particles that land in the solar neighborhood, in this donut shaped, very close to the solar neighborhood. And I assign the particles, the dark matter and the stars, that are now at redshift 0, so today, in my solar neighborhood, but they have merged in a very, very long time ago. And I look at their velocity distributions. So these are the histograms in galactocentric spherical coordinates, so VR, V theta, and V phi. And you can see that there is quite a close correlation between the velocities of the dark matter and the stars. Not only that, they are actually Gaussian distributed with more or less the same dispersion, which means that if you actually put these together, you will end up with something very close to the Maxwell-Boltzmann distribution. And the reason that this is true is because these mergers happened a very, very long time ago and have had enough time to relax and virialize. Then we're going to look into more recent mergers, because this is just like the boring part of the story. And to do so, we actually use Gaia. So Gaia is a space telescope that was launched in December 2013 with the goal of giving us the positional and kinematic measurements of 1 billion stars. It actually gave us 1.8 billion stars, which is quite incredible. And when I talk about positional and kinematic measurements, I mean 2 positions in the sky and distance, so that's 3 positions, and then 2 velocities or proper motions, so the 2 motions in the perpendicular plane. So this is 5D kinematics. The sixth parameter, or the line of sight velocity, is only provided for a smaller subset, which is in the second data release of 7 million radial velocities. The next data release is going to be available spring 2022, and this 7 million number is going to increase by order of a few. So this is the Gaia's awesome slide, where this is the limit of the accurate measurement of the distances of Gaia, and then versus, which is past the galactic center, versus this tiny circle where the sun is really the extent of the previous experiment, which is Hipparchus, that ran from 89 to 93 to get the same accuracy. So you can see that actually has been quite a tremendous development in the area. So in 2018, when the second data release actually was published, there has been a discovery of a very large merger that has happened in the Milky Way. And this is what it actually looks like. So this is where the sun is, or basically we live a little bit on the edge. And this is the merger that has been called the Gaia Enceladus, or the Gaia sausage. And it has merged into our galaxy and left these very elongated orbits of stars. And if anything, it actually dominates quite a bit of the stars here. very close to the solar neighborhood. So it is actually a very large fraction of the non-disk stars. About 60% of non-disk stars are actually coming from this one merger, which has happened somewhere between 6 and 10 billion years ago. Interestingly, in some of our simulations, we actually found similar mergers, not exactly one-to-one. So Gaia, for example, or the Gaia sausage, for example, actually has merged in between redshift 1 and 3. But this merger that I'm actually showing you actually merged in about 0.7. It's not exactly the same distribution. But we saw that for these types of mergers, which are not actually streams in the sky, but actually have lost some physical structure, there is a strong correlation today in the velocities today between the dark matter and the stars. In particular, the one I'm showing you here is in the histogram in the radial velocities, where there's like this double peak structure, which is quite different from the Gaussian that I was showing earlier. And the reason that we have this particular structure is because of the type of orbits that we have. So imagine if you have a circle and then or a sphere, and you're shooting kind of an arrow through it. The arrow does a 180 and comes back. As it goes in, it will spike at negative velocities, and as it comes out, it will spike at positive velocities. So these are very eccentric orbits. So we can see that for these types of mergers, dark matter and stars are actually quite correlated. And indeed, when we go into and see the data, we find a very similar structure, which means that we can expect that if dark matter is indeed collisionless, just like the stars, things will get correlated the same way. Now we can also look. One of the things that we actually found in Gaia is this new stream that we get to call Nyx, after the Greek goddess of the night. And it is about 250 stars that are co-moving here, and I will discuss them later. But their implications for dark matter is a little bit trickier, so we'll get back to it. Okay, so what we can do now, at least for the halo and the subhalo and the substructure, or the Gaia sausage components, is build the velocity distribution of dark matter as the sum of these two components. One thing, however, is that these fractions here, the contributions of these two distributions is not trivial. And in particular, because these mergers do not contribute the same amount of stars as they do dark matter, which means that we cannot just take the fractions that we get from the stars and plug them in. And this might get a bit technical, and I'm happy to discuss this afterwards. But basically, we find that the Gaia sausage, even though it contributes about 60% of the local stars, it actually ends up contributing about 42% of the local dark matter from luminous satellites. So there are a few caveats here and there. But the distribution ends up looking like this, where this is the histogram, this is the substructure here in blue, or the Gaia sausage. This is the distribution of the old halo, or things that I have virialized a while back. And we put them together and we end up with this solid black line here, which is quite different from the standard halo model, or in dash gray, or the Maxwell-Boltzmann distribution, especially at the tail. This has major ramifications on direct detection limits, and different experiments are affected differently, which is why it's very important to get it right. It's different, of course, for different theoretical operators of how dark matter and the standard model interact, and it would affect yearly modulations just because of the asymmetry of the whole distribution. So if we were to take a look at how this would, for example, affect direct detection, we can have these distributions here. This is the empirical one that we found, and this is the standard halo model. And before I discuss this, I would like to point out that this is by no means the final distribution. There are a couple of components that still need to be added, which I will discuss later. So as I mentioned earlier, the rate for direct detection is actually proportional to this integral of f of v over v, starting from a minimum velocity. And this minimum velocity depends on the threshold, the energy threshold of a particular experiment, and the dark matter mass. You can think of it as basically this is the lowest energy or the lowest velocity your dark matter particle can get for it to actually cause some kind of scintillation light for you to be able to see it in your detector. So if I wanted to integrate, for example, and detect a 10 GeV dark matter in a xenon experiment, the minimum velocity actually happens to be 567 kilometers a second, which means that if I initially thought that I have the standard halo model with the dashed gray, and then I realized that my distribution is instead this black line, this empirical line. You can see that the rate is going to drop because just of this area right here. However, if I was looking into 100 GeV dark matter, the minimum velocity is 95 kilometers a second, so I'm going to be integrating most of this distribution. Both of these distributions are normalized to 1, so they will end up with more or less the same answer. So this is my rendition of xenon one-ton limits, where here on the x-axis we have the dark matter mass, on the y-axis we have the dark matter scattering cross-section, and if we were to assume that the standard halo model, we will end up with this dashed gray limit, so everything above this dashed gray line is excluded, versus if we were to assume this new distribution, we would be excluding everything above this line here. So you can see that we might, in some places, it's like the change is actually by orders of magnitude, just because this is kind of like the exponential, very close to the threshold, so things kind of, these curves actually shoot up pretty quickly. And we might be, in some cases, we might be over-constraining, so we're ruling out more parameter space than we should be. So a couple of things that still need to be taken into account. First of all, we need to figure out what the correlation between the stars and the streams is, between the stars and dark matter. So far, I only talked to you about older mergers, so things that are very, very old prior to redshift 3, or things that are in the range of like about redshift 1. These two are correlated. Streams, however, they have not been established yet, and the reason for it is because they are still in the early stages of disruption. So there is a bit of a phase, a little bit between the stars that are very, very close to the inside, and then the dark matter that is extended. And the second thing is dark subhalos, which I will get to. But let's regress for a little bit, and I will tell you why I'm very excited about NIX. Well, NIX is this collection of stars that we actually found through a machine learning technique to figure out what stars that have merged into our galaxy look like. And let's go through its properties a little bit. Here, this is in kinematic, so VR, in galactocentric spherical coordinates, and V phi. The disk of the Milky Way, the disk stars, actually co-rotate at about 220 kilometers a second, which means that they would live about here. NIX actually is prograde, so co-rotates with the disk, but also has a non-trivial radial velocity term. So this is why it is sitting right here. If we were to plot it in space, so X and Y, we would see that there are a lot of stars that are actually going at an angle. The sun is rotating like this, so this is a lot of arrows that basically look like this, where the sun is going to rotate like this way, and a lot of these stars are moving into the galaxy. And these stars actually extend above at least the thin disk to maybe include the thick disk. So you can see here that this is the disk of the Milky Way, and it's going to go, we have a lot of the stars going up and above and below. So so what can we learn from here? Well, there are two theories about what actually could cause some stars to actually behave like this. One of them is that if it's a disturbance in the disk, so we have the disk of the Milky Way, something hits it, it puts a lot of these stars into these very strange new orbits. Or, and this is my fingers crossed favorite interpretation, is that this is a merger, so something hit the galaxy and actually is kind of co-rotating with it. And I will explain why. But yes?
I'm having difficulty differentiating the two.
Yes.
Phenomena, two causes.
Yeah. So let me say that again. Yeah. So basically, theory one is that we have, these are stars from the disk, and then something fell in. For example, it could be like a subhalo or something, and then put these particular disk stars into very different orbits, which is why they look the way they do. Or we have the disk here, and then we have stars and dark matter. They kind of came in and hit this. And the key difference is dark matter here. Okay, so yeah.
So this is, in a sense, it is heating of the stellar population.
Yes, so this one is the heating of the stellar population of the disk. Yes.
Why is the second one not heating?
It would also heat, but some of these, so basically it's the origin of the stars that we call NICs. Are they actually disk stars, like this, or are they stars, accreted stars? Yeah. And the reason that this is interesting is because we applied this whole machine learning pipeline onto one of our simulations that has a merger that looks like this. And this is what the simulation looks like. So we have this disk galaxy here. It's going to be co-rotating, and you will see that it's going to be hit by a merger here. So see this merger here, it comes in, and kind of because it came in while it's co-rotating, kind of gets dragged with it. I will now discuss why it's important for dark matter, because such a merger is expected to bring in what we call a dark disk. Of course, dark disk I think has a different interpretation / different connotation, but basically I want to talk about the co-rotating component of dark matter. And we really need to understand if that's the case and how much dark matter that would have brought in. So there's this paper from Justin Reed back in 2008 that says, as satellites are torn apart by tidal forces, they deposit both their stars and their dark matter into a thick disk. The latter point is the key new idea presented in this work. A dark matter disk must form in a lambda CDM cosmology. Some people might argue that must form is a little bit strong, but basically this says that they ran a lot of these simulations and they found that you can get a lot of these prograde mergers into what your lambda CDM galaxy looks like. So why is this interesting from a point of view of dark matter? Well, if, for example, I have a component that is co-rotating, I would expect that their velocity compared to us in heliocentric frame is going to be very close to 0, which means that this is not going to affect the low mass dark matter. That's going to be unchanged because we're still integrating that part. But for the high mass dark matter, that might actually change our limits by quite a lot. So there was this follow-up back in 2008 of the same paper that actually discussed this. So let's focus on the black line. This was Xenon 10 back at the time, where dark matter mass here on the x-axis, dark matter scattering cross-section. And this is the distribution, the standard distribution that you're used to. But if you end up adding a different, like an extra component coming from this dark disk, you would actually start affecting this high limit just for that same reasoning. And you might be excluding more parameter space than you should. So there is a lot of work to do here. In particular, we still need to understand if NICS is indeed option A or option B. If it is option B, then it has some dark matter ramifications. And the way to do that is through an observational study. So we go and measure the chemical abundances of these stars to figure out if they're consistent with disk stars or are they actually accreted stars. We need to figure out how to correlate dark matter and stars and streams, estimate the relative contribution of dark matter. And also, this is the last caveat that is not NICS related, but basically, we have not really discussed the contribution of dark subhalos. So everything that I've been talking about up to now, we can use the stars as tracers for the dark matter, but for small enough halos, there are dark subhalos because they do not have any stars. So we need to get very creative and figure out how to estimate those. And we're still working on that. So using Keck and Magellan, I really wanted to go to both. I had observing time on both. Magellan here is in Chile. I mean, who wouldn't want to go in person to this? Well, unfortunately, pandemic, so we had to do it remotely. We lost a few nights, but still, at least we got some data here. We observed a selection of NICS stars. The majority of them are actually consistent with thick disk stars, but we have a very interesting low metallicity stars, or tail of the distribution, that is very, very hard to explain with thick stars. So there might be some accreted component there, and we're still working on this because analyzing spectra of stars apparently takes a very, very long time. And thankfully, I have very amazing observer collaborators who are doing that for me. OK, so there is a lot to do and a lot to unpack. And now the rest of the tour of the Milky Way is going to be a little bit faster, just because the solar neighborhood is so interesting. So let's move on to the galactic center. Indirect detection. Indirect detection of dark matter, it annihilates or decays into standard model particles. For example, standard model particles could be positrons, photons, sometimes even anti-helium. There are searches of that. And the way that we can estimate how much of them we can see in the solar neighborhood, we need to know what is the density of dark matter at the center of the galaxy. So the term that we will be using a lot is this thing called the J factor, which is the integral along the line of sight of the density or the density squared of dark matter. So to motivate all of this, I will just look into one search of one particular particle model. So a simple extension of the standard model. Just you add just a new particle chi here. It's expected to be in the TeV scale, so you can't really see it in colliders. But again, this is just to put everything into context. This is applicable through any of your favorite indirect detection searches. So how can we look for this particle chi? Well, it's going to annihilate, and there is Sommerfeld enhancement and a very, very complicated cross-section calculations here. But then it will emit photons that can be detected in one of these Cherenkov detectors, HESS, which detects photons from 30 GeV up to 100 TeV. So to estimate the number of photons that we would see, we would actually kind of calculate the flux, the experimental efficiency, and the exposure. So there are three separate terms that I would like to emphasize here. The cross-section of this process, and the reason that I picked this is because a lot of my friends actually, two of my office mates, one at Caltech and one back at MIT, actually calculated this process, and it involves a lot of loops, and it's very difficult. So I know how hard they worked on this, and they ended up with a cross-section that actually, that if you were to estimate its uncertainties, is about 10%. Effect on the limits. Then experimentalists are doing an amazing job, where the experimental uncertainty actually is down to 25%. And you can see where this is going. The astrophysics part is, with a very crude estimate, 50,000%. But like, it's a lot. And some people told me, well, that's not fair. But anyways, there are different ways that you can estimate this, but basically it's a lot compared to everything else. So why is this a lot? Well, it's because I'm integrating the density of dark matter along the line of sight, and I don't know what the density profile of dark matter in the Milky Way actually is. So here it could be an NFW or an Einasto profile. This is density as a function of radius. Or it could be a Burkert or something very chord. Whoops. Yeah, okay. It was too much for the pointer. We could, so basically we don't know which one is favored. I mean, some of them are a little bit more likely than others, but still. So the way that we can actually look into limits this way is then by assuming very different profiles and looking at the limits, how they vary with these. So for example, here, for that same process, this is the experimental paper. On the x-axis, we have the dark matter mass. On the y-axis, we have the dark matter scattering cross-section again. And basically, this gray line with a lot of peaks, that is the theory line that is calculated. And everything above a certain horizontal line is excluded. So for example, if I was to assume a 2 kiloparsec core, I have the blue line. Everything above that blue line from the theory line is excluded. So I would be excluding something about 2 to 3 TeV of dark matter, as well as like this tiny bit over here. While if I were to assume an Einasto profile, then all of that is excluded up to 10 TeV. Yes?
How can you have a core
Yeah.
when you have
when you have CDM, with the baryons, actually, they do kind of give you some coring of Milky Way-sized galaxies.
Are they 2 kpc?
Yeah, no. I think that 2 kpc is a bit high. But, yes. So you end up, so yeah, in the experimental paper, they actually considered quite a few different size cores. But you can look at simulations and figure out what the size of your core is. Empirically, we don't really know within CDM, what it looks like. Oh, the Sommerfeld enhancement. So basically, you end up with a lot of these, and then they kind of add up into resonances, and that's why they look like that. Yeah. So this is just to motivate that we really need to understand the density profile of dark matter. And in particular, we need to figure out where do we live. And the goal is to narrow this down. And just, the breaking news is that I still don't know what the answer is, but I have an idea of how to do it. We might get it from the data set of next year. So one way that we can do this is by measuring the escape velocity of dark matter, of the stars, which tells me about the Milky Way potential, from which I can deduce the dark matter density profile. And quite a few assumptions actually go into this process. Unfortunately, with Gaia DR2, which is the data that I had at hand, there isn't much of an extent into the 6D kinematics that I was talking about earlier. So everything is very, very close to the sun. With Gaia DR3 next year, hopefully, there will be a little bit more of an extent, so I can measure the escape velocity at different radii and then be able to construct the dark matter density profile. And this is just to show you that the dark matter density profile, this is the escape velocity as a function of the radius for different profiles, and things actually do look very different. So one way that we can do this is by measuring the escape velocity. And this is just mock data to illustrate the point that I would like to make. So the goal is to fit for the escape velocity. And as we studied in introphysics, the escape velocity is going to be basically the highest point at which the stars are still bound. So most of this distribution is within this escape velocity here that I'm simulating at 500 kilometers a second. But there are also a lot of these outliers. These could be badly measured stars or just hypervelocity stars that are just not bound. They're just passing by. So since 1990, there's this paper by Leonard and Tremaine of how to measure the escape velocity. And they actually fit it with this functional form of v escape minus v to the k. So you actually fit for the escape velocity, this term, and for the slope. Of course, that's not easy. There are the complications that you need to take into account the errors in the measurements, and we can do that. We can just kind of fold them in. The presence of outliers, these guys here, we take them into consideration as well. You can just like model them separately. But also the thing that my collaborator Tongyan Lin and I actually talked about and thought about is the presence of multiple components. So this is the true distribution that I used to generate this. So we have the halo here in red, and also we have the Gaia sausage, because we now know that both of them exist. And the Gaia sausage is actually a non-trivial component of the local stars. So we really need to be able to actually take that into account when we model this. So when we want to fit the tail of the escape velocity, we're going to fit this above a certain minimum velocity. So if my minimum velocity is it's pretty high, like 400, then I am dominated by a single distribution, and having this being just like with a single function should work. However, most of the time in the literature, people assume that minimum velocity of about 300 to increase statistics, where you can see that you might actually start getting two components on top of each other, fitting in with just one, and just the fit is going to be bad, and a lot of problems are going to happen. To illustrate this, basically, if the real function is dominated by a single distribution, and then you are fitting it, again, these are just mocks with some errors, you will end up with an answer within 1 to 2 sigma, so it's something very acceptable. If it is indeed two functions and you fit it with only one, you end up with a wrong answer, as expected. Or the one way that people in the literature actually have tried to solve this is by putting in artificial priors on this distribution here of the slope k. And you end up with basically biasing your results in every way, and it just doesn't make sense. So artificial priors do bias your results, and you shouldn't do that. So what we did is, this is with Gaia GR2, is to actually fit this distribution with multiple functions. So this is with single function, it looks pretty bad. This is with 2 functions, things look a bit better. We can even use 3, and this is because there is a bit of a disk component in that first bin, of course. So I'm not going to say we just looked at them. We did a statistical test to figure out where the best fit distribution is. And then we can redo this as a function of the minimum velocity. And you can see that things are converging, right, as expected. So when you go higher into the minimum velocity and you look at the posterior distribution of the escape velocity, it has to kind of converge towards the right answer, because at pretty high, 1 fit or two function fits, they should give you the same thing. So from this, we have our measurements of the escape velocity here. And then we can compare them with the measurements from the literature, which use some kind of biasing of the slope. And then we can interpret them, because we don't have them at different radii just yet, we can interpret them as different measurements of the Milky Way potential, so we can translate them into a mass of the Milky Way, which tends to be 7 × 10⁻11, so a bit on the lower end of what is expected. This will be a lot more interesting in about 6 to 9 months, when we can actually use the full density, we can use the full data from EDR3 to get the full density profile. So it's something that we're looking into, and we're currently using simulations for. Okay, so moving on to dwarf galaxies. Yes?
Okay. So the mass of the Milky Way, the M200, that's dark matter environment, and it's 2 × 10⁻11.
Yeah.
Is the baryon fraction of that consistent with Milky Way size halos in simulation?
Oh, is the baryon yeah, so to actually get to this number, I mean, the baryon fraction of that is about 1%, right? Like, it's about 10 to the 10.
Yeah, but is this what we see?
Yeah, so...
Do you just see 1% of that for this guy?
Yes, pretty much. It's about 1%. So, for example, actually to get to this number, we had to assume a Milky Way potential, and for that you kind of like build the Milky Way component by component. So we added the bulge, the disk, with the best fit parameters that we actually have from observation, and then a dark matter halo that we actually start fitting for, and that will be dominating the mass. Yeah.
And so that's only about the factor of 10 or so compared to the LMC.
Oh yes, the LMC is pretty large. Yeah, yeah, and yes, but one thing that we did not take into account when we modeled the escape velocity here and translating the escape velocity into a mass of the Milky Way is the effect of the LMC, which is something very important that needs to be done. This is just, well, it was like kind of like the first order of doing things, but the LMC is going to not only affect the potential to kind of get to this number, but also it might be the one responsible for these high velocity stars and the tail and everything. So that needs to be taken into account, absolutely. Does that answer your question? Cool. Okay. All right. Dwarf galaxies. So we keep driving around the Milky Way. What are dwarf galaxies? Well, there are these satellites of the Milky Way that are captured by the Milky Way somewhat right here. And we have quite a few of them that we keep observing, which is great. The blue ones are the confirmed satellites, and the red ones are candidates. So there is just a lot of them that we're building, especially because of new surveys. So we've discovered quite a few in the last decade or so. So why are they interesting from a dark matter point of view? Well, it's because we can look at their profile, or the stellar distribution of these stars, and actually argue whether or not they are from a cusp or a core. So this is the density of the dark matter profile as a function of the radius, and we can see / argue that a lot of them actually would favor a core. Why is this interesting? Well, baryons can actually help form a core, that's true. But for these smaller systems, there are not that many stars or gas. So it's very, very difficult to form such cores. And one way that you can do that is by having dark matter self-interacts. So if you start with the cusp, there is a very high density of dark matter, and then you end up with a lot of these processes that kind of share the energies and things, and basically pushes a lot of the dark matter out, and it transforms the cusp into a core. So, of course, this is a non-trivial task, in particular because when you do G's modeling to end up with this, you have to make a lot of different assumptions. You have to assume that the system is in equilibrium, there's no tidal disruption, the distribution is spherical, etc. So what my collaborator and I actually started doing was trying to think about the effect of binaries. And then we realized it was very difficult to actually, in the best of cases, obtain the right distribution with very few stars. So basically what we did is we built mock simulations of the simplest dwarf galaxies we could think of. So something that is isotropic, spherical, there is really nothing going on with it. And the true distribution is this dashed line here in black, where this is the density profile again. This is radius. And then we tried to select some of these stars and add some error to our measurements and see if we can actually reproduce what we put in through the common pipeline. And we realized that no, it is actually very difficult to do so. And in particular, it's very difficult to do so without a lot of stars, in this case, about 10,000 stars. We can look at the posterior distribution of the inner profile, which we can actually parameterize here as a function of gamma. This is basically the modified of n of w, where a cusp is gamma equals 1 and a core is gamma equals 0. And you can see that the posteriors that we get for 20 stars, 100 stars, 1,000, and 10,000. And this is for different velocity measurements. And basically, we can actually rule out gamma equals 1 in favor of gamma equals 0 with very, very high number of stars. So 1,000 to 10,000 stars. Just highly non-trivial. This is for a quite massive dwarf of 10 to the 9 solar masses. If I wanted to look at an ultra-faint, so a couple of orders of magnitude below, oh, here we go, then things will get even worse, especially that basically even with 10,000 stars, if you have badly measured velocities, you're not going to be able to get this. And the reason for it makes sense because the velocity dispersion of your system is also about 5 kilometers a second. So if your error is about the same as their dispersion, then you're not really getting good results there. This will affect the J factors that we get. And in particular, you tend to overestimate the J factors. This is the massive dwarf for different errors and different number of stars. And for the ultra-faint, you can underestimate the dark matter. And it's because the velocity dispersion that is from your errors can be explained with just the size of the system. So no dark matter actually would solve it, which is why these two error bars are here. But with high enough statistics, you are able to get the right answer. Why is this important? Well, because the measurements that we use right now for dwarf galaxies in direct detection, here we go, are actually dominated by a few of these systems, and they are actually here sorted from the highest J factor, and this is in log. So you can see that these 5, for example, Ursa Major, Segway 1, etc., actually have very few stars, 20, 70, 59, with very small dispersions, which means that they will be affected by very small errors in the measurement. So it's very important to get this right.
Where did these J factors come?
These ones, wait, which paper is this? Oh, I thought I cited it. Yeah, I have, these are the measurement ones. I will look into it and tell you, but I have it somewhere. And I think this is the one that was referenced by Fermi, which is what I used, yeah. It's outdated? Yeah. But the number of stars has not really increased by that much, has it? No. Okay.
No, so this is it.
Yeah, okay. If there was a better reference, I wouldn't want to know about it, but yes.
This is the Ackermann et al.
Yes, the Ackermann et al. Yes, that's the paper. So we need to do better about this, and this is just to motivate for why we really do. But just once we have the density profiles of these galaxies under control, we can actually explore a lot of different things. And in particular, for example, our high-resolution simulations can actually now generate alternative dark matter models, for example, dissipative dark matter, and the profiles for dissipative dark matter are actually going to be extra cuspy beyond the CDM, which means that if we understood this density profile, we're able to rule out these parameters. But of course, the way that we model alternative dark matter in simulations is still a question. So I think it would be very interesting to have particle physics and simulators actually talk to each other to figure out what are the right models to be modeled for these large-scale simulations. Okay. And finally, and briefly, let me tell you about streams and how they can tell us about dark matter. So what are streams? This is the dark matter, this is the Milky Way, and we have galaxies that fall into the Milky Way. And because there is a gradient in the gravitational potential between like these two sides, these stars kind of get stripped and actually have like these different orbits. So we have like the leading arm and the trailing arm here. And a picture from the Sloan Digital Sky Survey back in 2007 would look like this, where we have like these overdensities from these particular streams. This is GD1, the Orphan stream, Sagittarius, and Pal 5. And let's take a look at GD1. So GD1 with Gaia DR2, the second data release of Gaia, actually has been extended just because we have amazing data now. And importantly, with the work of Price-Whelan and Bonazza, they actually found that there are gaps. So these are like the underdensities of the stream. Why is this interesting? Well, it's because one way that you can explain such gaps is that you have the stars here, and then you can have a dark matter subhalo that you do not see, so it doesn't have any stars, kind of go right through and gravitationally pull some of the stars. So, which means that this method can actually tell you and determine the size of these dark matter subhalos. Indeed, Bonazza et al. In 2019 tried to fit this with this GD1 perturber, so the time that actually it came in and pulled these stars out, its mass, the impact parameter, its velocity, and its scale radius, and put everything together into this plot, where on the x-axis here we have the size of the perturber, and then on the y-axis we have its mass. So this is the best fit region, which is consistent within 3 sigma of the lambda CDM subhalos. So it is an interesting strategy that is going to be telling us about dark subhalos if we need to know what they are. But to be able to do better than this, we really need to find more streams. We need larger statistics. And now that we have a lot of data, one way to do it is to actually automate the search for streams. And one thing that we've done with my collaborators is actually build this automated search for streams. So this new algorithm called Via Machine, which is based on anomaly detection. So it takes the distribution of stars here, and then it models what it thinks the control region is, or the background, what it expects, and looks for bumps, just like we do in the LHC. And then when you pick like the most significant stars for GD1 in that GD1 region, you would actually see it by eye. Here, in this first work, we actually just showed GD1 just because it's easy to find. You can actually see it by eye. You can discover it by eye. But this is just to establish the algorithm, and we're now doing a full sky scan, and we will be releasing a list of potential streams or potential stream candidates that will be followed up. So we can take this. This is the stream that we find. This is the one found by Bonazza and Price-Whelan. we can get at least definitely get this gap in this automated fashion, and this one there's a decrease in the density distribution. The tails we don't do as well. It's because they're over dense, so the algorithm kind of flakes out. But we're currently kind of studying and improving this algorithm so we can test it on GD1, we can test it on simulations, make sure that it does what it's supposed to do. And in particular, actually get the false positive rate, which is very important. And then we apply that to the full Gaia DR3, EDR3, and the full DR3 to figure out where are our streams. Okay, so there has been quite a bit of a tour. So today what I wanted to argue is that it's very important to map out the dark matter phase space distribution. It's very important to understand it at different spots. And every single one of these, especially coupled with simulations and with Gaia, can tell us a bit more about what the dark matter is and how that kind of correlates directly into our detection and prospects of discovering dark matter. So I will leave you with my favorite thing, which is Nyx, the Greek goddess of the night, coming out of the Milky Way. Thank you.
Okay, questions?
Yes.
Sorry, I should go first. Is there somebody I should call you?
Okay.
Yeah.
Hi, Lina.
Yes, hi.
Hey, Rick. Oh.
If you don't I turn the lights on.
Oh, yes.
Yeah, I enjoyed your talk a lot.
Thank you.
And I learned a lot of things. So I'm going to ask you, but I'm a condensed matter person.
Okay.
And so when I saw those streams, those are very exciting.
Yes.
The idea of seeing streaks like that. And that so the ones with the gap.
Yeah.
I guess, water, when it forms a stream and it starts to get thinner,
Yeah.
there can be these capillary instability.
Yes.
Do people ever think about these things in those terms?
Yes, they do. So one way that we can actually get these gaps is by just the chaotic orbits of the whole galaxy. And actually we have about 2 or 3 of them that get very close to the disk of the Milky Way, and they have some of these gaps. The thing is that we cannot really think of dark matter as an explanation for those. This particular stream, the reason that it's actually the most likely that it's caused by dark matter or something else is because it's very high up, so very far away from the disk. So the disk are where the whole mess of chaotic orbits. So this one is it's 10 kiloparsecs away and quite high. So we don't think that it actually interacted with the disk of the Milky Way, and that's why it's quite unlikely. But you're right, it's very important to take those into account. Yeah.
What are the prospects of using some of this data for actually testing more exotic dark matter models?
Yes.
Self-interacting, etc.
Is self-interacting. Yes, so actually, for example, for the streams here, now one of my students actually has this project where we're looking into a student and a postdoc, looking into the stream evolution in potential from, for example, if you have dark matter self-interacting. So if you have the merger coming in, basically the dark matter from that self-interaction from the merging halo is going to interact with the dark matter that is in the halo, and that will cause the disruption to be quite different. But of course, to quantify that, we're looking into simulations.
Do you think it has the potential to actually rule out potential dark matter interactions?
That would be great, yeah, but it has not. So basically, this is a little bit of a new area that has not been really discussed that much before. And the reason that now is the time is to do it is because now we finally have data. We have kinematic data from Gaia, and we also have simulations that actually can do this quite faithfully. So it's definitely, I think it will have an effect, but we need to actually do it to figure that out. Yeah. So it's interesting.
Any other questions? Yes,
Does the presence of dust in the galactic disk and the center distort the statistics from surveys like Gaia?
Yes, a little. No, it's not too bad, but yes. So we have to correct. For example, we have dust maps, and we have to correct for that when if you rely on photometrics. So anything that is actually, the photometrics of the stars. If you use that to kind of select, for example, a particular magnitude of stars, then you have to take into account the dust. The thing that is a little bit even more complicated is crowding at the center of the galaxy. So as I was showing earlier, technically Gaia can actually see past the galactic center, but the way that Gaia actually works is by kind of taking pictures, and it's a space telescope, so it takes a picture and then kind of does a full tour, it takes another picture and says, okay, the star was there and now it's there. That's what the velocity field is. But if you do that at the galactic center where there are a lot of stars, then it's very easy to confuse, wait, that star, is it now this one or that one? And then you end up with bad measurements and everything. So towards the center of the galaxy, things get a little bit dicey. Yes.
Gaia, visible light, or does it have...
It's optical, yeah.
Can I ask you?
Yeah.
So the assumption that dark matter and stars, basically stars trace dark matter.
Yes.
When it comes to these kind of things that can just fly through, right?
Yeah.
So in the very inner region, it is possible that the whole dynamics of the stars are set by the stellar population. And the role of dark matter is minimal in the dynamics of those stars, right?
Mm-hmm.
So I'm thinking, say, progenitor for globular cluster.
Okay, yeah.
Right?
Yeah.
So how reliable then is the assumption that what I expect the velocity dispersion or the velocity distribution function of the dark matter to mirror what we see in the stars?
Yes.
And what kind of an error does that introduce in the interest?
So yes, so that's a very good point. So this only holds, first of all, in if you assume that dark matter is collisionless, right? And indeed, we ran like a self-interacting dark matter simulation, and you can see that the distributions are widely different, even with a small cross section. So there are a lot of it's kind of like a lot of bit of a coincidence for why this works a little bit. So at first order, you have stars and dark matter coming from the same object, they have the same initial conditions, and you have gravity, and you kind of let them be, they will end up in more or less the same place. The reason that's not exactly true is because the stars kind of are very deep in the potential well, and you have the dark matter extending, right? So the dark matter on the outside, why would it trace the inner stars? The reason that it works, that we verified with simulations, is because we kind of live very, very close technically to the center of the galaxy, which means that as the satellites actually fall, the first thing that you're going to etch out are the dark matter on the outside. And then by the time you're disrupting the stars and disrupting them into debris flow, really, you're only tracking the inner dark matter, which is why it works, right? There are other complications, but anyways, that's basically majorly why this particular setup works and works here. For example, if I was doing this at 100 kPa, it wouldn't work. And this is also why it kind of somewhat fails for streams, because you're just starting the disruption process, so it doesn't really mirror it when you go into debris flow. So actually disrupt it quite a while, then this holds. Yeah. Mm. Yes.
Okay, one last question.
So again, if somebody else wants to
Does somebody else?
So in regards to your anomaly detection stuff, so it definitely makes sense finding these streams. Have
Yeah.
you considered applying techniques like anomaly detection to detect other structures, maybe something like a Gaia sausage or something?
Oh, like a Gaia sausage, it's actually a bit difficult because these structures are quite extended in velocity space. So right now, I have another student actually looking into it, but applying something like a PCA, principal component analysis, or autoencoders, to just so it's slightly different from the anomaly detection that we have here. But we can actually use this to find overdensities like dwarf galaxies or globular clusters, so some things that is extremely anomalous very quickly. And yeah, we're kind of looking into it now. Pretty localized, exactly. For this particular method, it has to be a bit localized in some kind of space. Yeah. Mm-hmm.
Okay, last question.
Yes.
Obviously, I was a little disheartened when you said it was going to be so difficult to be able to differentiate NFW, but
Oh.
given the huge. Yeah. Is there there anything encouraging you could say about to that one? Clearly Gaia is just, LibreOffice, but it's...
Oh, yeah. There is a future. Yeah. So, for example, I think with JWST, it's going to be an IR, which means that we will be able to actually see the stars very, very close to the galactic center. It will be a lot of modeling, so it's not an easy task, but I think we'll be able to get there. Yeah. So it's not as bleak as it made it sound. Yeah.
Great. Thank you.
All right. Thank you so much for having me. Thank you.